Okay, so today we're going to talk about graphing linear systems of equations. So previously we've been talking about how to graph linear systems of inequalities. And with linear systems of inequalities, our solution set is the place on the graph that is shaded by both inequalities. So any point inside of the double shaded region would have been a possible solution or ordered pair that satisfies both inequalities. Now we're going to kind of take a step back. This is possibly easier than systems of inequalities, and we're just going to look at systems of equations, meaning just lines on the graph. And we're looking for essentially where the two lines intersect with each other, and that's going to be the solution that satisfies both equations. So this is very similar, the same way as when we graphed linear systems of inequalities. The only thing that really changed is now we're graphing two on the same grid. Linear systems of equations is defined as two or more linear equations with the same variables on the same graph. So if we graph two lines on the same grid, that is a system of equations. A solution to a system of linear equations is just any ordered pair that satisfies all the equations in the system. Another way you can think about it is the place where the lines intersect. So, we're going to look at a couple examples of linear systems of equations, and we're going to talk about the different types of solutions that are possible in a linear system of equations. So let's go ahead and take a look at the system A. I labeled this system of equations A, and we're going to find the solution to this system. Okay, so with the system of equations A, I have x plus y equals 4 and negative 2x plus y equals negative 2. Can I graph these equations as they are right now? No. What do I need to do? Put them into slope-intercept form. Then I heard somebody else say what the first step to getting this into slope-intercept form is. We're going to subtract x on both sides. So I've got y equals 4 minus x, which I'm going to rewrite as negative x plus 4. And this will be the first equation I graph onto my grid. Raise your hand if you can tell me, what is the first thing I do to graph this? I'm going to go with Bailey this time. Start at the y-intercept of 4. Perfect. Now, raise your hand if you can tell me what the slope is. Giselle? Negative x, which means our slope is negative 1, which we can write as negative 1 over 1. So anytime you have a slope of a whole number, you're either going to go up and right or down and right. Because it's negative, we're going to go down and right. Down 1, right 1. And because it's a whole number, you're always going to go right 1. If it was a fraction, you would go right by the denominator. But in all whole numbers, you're going to go right 1. Logan?
Oh, why are we closed? Because it's an equal sign?
Wait, yeah, so the points are going to be closed because it's an equal sign?
No, why?
Why?
Oh, I don't know.
Oh, yeah, wait.
He's asking why.
Okay. The points are closed just like when we have greater than or equal to or less than or equal to. We do closed points. It's only when it's less than or greater than that you do open points.
Okay.
So with all lines, if it's an equal sign, you're just going to do normal closed dots. And I've got all those points. I went down and right 1, down 1, right 1 until I got to the end. Then I went back to the y-intercept and I went up and left. Up 1, left 1. And we can graph that line. Any questions about how we got this line graphed? Okay. I'm going to go ahead and quickly open up a tab of Desmos, and I'm going to graph it in there as well. Just type in y equals negative x plus 4. Hopefully we all have Desmos open, so go ahead and type that in. And we'll come back to this line in a second. I'm going to make it blue just to match my paper. And then now in red, I'm going to do the other one. Again, we've got to convert it into slope-intercept form. Raise your hand if you can tell me my first step. Bailey. We're going to add 2x on both sides. So I get y equals 2 plus 2x, or 2x plus 2. Or wait, negative 2. Sorry, I forgot. I didn't bring down my negative sign. Always make sure you bring down the negative sign whenever you bring down a term. So this is a negative 2, which means it's y equals 2x minus 2. So now I'm going to go ahead and plot my y-intercept of negative 2. My slope is a positive whole number, so I'm going to go up by 2. And because it's a whole number, I'm going to go right 1. So up 2, right 1. Up 2, right 1. Up 2, right 1. Up 2, right 1. And then we're going to go back to the y-intercept and go down to left 1. And you can see those points form a line. So I'm going to go ahead and graph the line. What do you notice about these two lines? They intersect with each other, exactly. So that point of intersection is the solution to this system of equations. Just like where we had system of inequalities, where the shaded regions overlapped with each other, and that was the solution set to the inequality system. Now with just lines, we're only looking at where the two lines intersect. So take a moment, look at that intersection. Raise your hand if you can tell me what the solution to this system is. Kason. 2, 2. X is 2, y is 2. Perfect. So that's one way you can find a solution to a system of inequalities, is by graphing them and seeing where the two lines intersect with each other. Okay. Go ahead and open Desmos back up. And then we're going to put the other line on the grid. Y equals 2x minus 2. And you should see, and I'm going to make it in red, that this line intersects with the other line at 2, 2. And that's one way you can identify your solution in Desmos. Another way that you might end up seeing questions ask you to identify your solution. Remember that the whole point of this is that we're trying to see what the y value, or when the y value is the same when you plug in the same x value. So if I plug in 2 for x everywhere I see it, the y value that outputs should be the same for both equations when I plug this x value in. So when I plug in 2, both of the outputs for both of the lines are 2, meaning that they share a solution at where x is 2, y is 2. Another way you can see that is by creating a table. So hopefully everybody has both of these equations typed into their Desmos calculator. Go ahead and click the gear button, edit list, and then there's a table button next to one of your equations. Go ahead and click create table, and it's going to create a slightly different type of table than the ones you've seen before. There's no x1, there's no y1, it's just x, and then the expression that is equal to y. Y equals negative x plus 4. So instead of putting y here, they put negative x plus 4 because they're equal to each other. And you'll see that it basically is plugging in all these x values and telling you what the y values are for each of them. So if I plug in 0 for x, my y value is 4, which makes sense. If you look at the graph, the y-intercept is 4. What we're looking for is where a certain row, a certain x value, produces the same y value for both. And the only way you're going to be able to see that is by taking the other expression. I'm going to copy it. You can just rewrite it. And then clicking the top of your table, and you'll see there's almost room for a third column. Click the header of that third column and either type or copy and paste that equation into the third column. And now it's plugging in the x values for the second expression. And it's telling you what the y values are. So when I plug in -2, I get -6, and so on and so forth. And you can notice that there is a certain x value in this table where the two y values for both are the same. And this would be how you use a table to see. And you might see a question on your test where they give you a table where two expressions are entered, and you have to answer which row shows the solution to this system of equations. And then maybe they'd label them as row 1, row 2, row 3, row 4, row 5. And you'd say the fifth row is where my solution is for this system of equations. Any questions about this table? It's just another way of getting your solution to a system. All right, then we're going to go ahead. Any questions about this? What type of solution? Or I guess I'll go ahead and say it. It's kind of a weird question. This is an example where your system of equation has, yes, Alyssa?
How do you combine the tables?
Oh, no problem. To get the second table, you can't actually click the gear. You have to, when you have just one in there, you click the top row, and then you click to the right of the top row and into the second, or I guess the third header, and you type in, or it's -2. You type in the other expression, 2x minus 2, into the third column. And that's how you get them on the same table. If I just tried to click gear again, it's going to make a brand new table. And we want to be able to compare them with each other, so that's why I did it like that. Perfect. Okay. So in this situation, there's only one place on the graph, or one ordered pair, where they cross. So we say, in this case, there is one solution. On a table, there's only one x value, or the two y values are the same. On a graph, there's only one place where they cross. Any questions about the situation where the lines cross exactly once and there is one solution to my system? Awesome. So let's go ahead and look at B. So this one again, we're going to have to rewrite in slope-intercept form. Raise your hand if you can tell me the first step to getting this into slope-intercept form. I'm going to go with Elias. We're going to add 3x on both sides. Sorry, it was out of frame. So I added 3x on both sides. And now I get y equals 3 plus 3x, which I'll write down here as 3x plus 3. And this is the first equation in my system. I'm going to start at my y-intercept of 3, and I'm going to go up because it's positive, up 3, and right 1 because it's a whole number. If there's no denominator, then I'm just going to go right 1. Up 1, 2, 3, and I'm out of frame of the grid, so I'm going to just stop there. And I'm going to go back and reverse. Down 3, left 1. down 3, left 1. And I can graph my line. And there's the line for my first equation in the system of equations. And now I'm going to do the second one. And maybe you notice the first step to graphing this or to rewriting this equation in slope-intercept form is the exact same. Add 3x on both sides, and I get y equals negative 2 plus 3x. So I'm going to rewrite that as 3x minus 2. Okay, have a great day. And I get 3x minus 2, and I'm going to graph that one. My y-intercept is negative 2. My slope is 3, so I'm going to go up 3 and right 1. Logan?
I noticed something about the lines.
Oh, what do you notice about the lines, Logan?
They are parallel to each other.
They are parallel to each other. So what do you think that means about the solution?
There's no slopes.
They have the same slope, and yes, Giselle, there's no place where the two lines cross. Therefore, there is no solution because we're looking for the place on the graph where the two lines intersect with each other. And since there's no place where they intersect with each other, there is no solution that they share with each other. There is no x comma y pair that both lines are going to cross through.
Can we do the next one by ourselves?
Thank you.
Yeah, let's try to do it right.
Real quick, I'm going to type these two into Desmos. 3x plus 3 and 3x minus 2. And you can see that these two lines are parallel. They never cross. And if I create a table and I type in the other, it does not matter how many times I push enter. There will never be a place where these two lines have the same y value for the same x. So that's how a solution would look on a table. There's no point
Okay.
where the x's and the y's are the same.
So Mr.
Why don't you go ahead and, yes?
Doing the second one, I mean the third one.
Okay, so hopefully you tried, or at least you started to try to do the next one.
Is this no solution, or is it like
Let's go ahead.
every point?
Very true.
Crosses out.
Gonna add x, y equals 2 plus x is my first one, which becomes x plus 2. And I'll graph that. 2 is my y-intercept. My slope is 1, so I go up 1, right 1, up 1, right 1.
All possible solutions. All real numbers.
Then we're going to do the second one. Negative 2x plus 2y equals 4. Going to add 2x on both sides. I get 2y equals 4 plus 2x. Going to divide everything by 2. And I get y equals 2 plus x, or again, x plus 2. And I'm just going to graph the same exact line because, as you guys so astutely noticed, they are the same exact line. So, thinking about our solution is where the lines intersect with each other. What do you notice about these lines?
All real numbers are infinite.
They are right on top of each other. So every single point on the line is a solution or xy pair that they share. So there are infinitely many solutions that they share. And I want to take a moment here to describe the slight difference between infinitely many solutions, which is how we're going to describe this system of equations,
My pups are out.
and all real numbers. So this I would not describe as all real numbers technically, because we're describing XY pairs, which another word for XY pairs or ordered pairs is solutions. Solutions is another word for a point. So when we're describing the points that are solutions that these lines share, there are infinitely many points that they share with each other. But we're talking about not just one number when we're describing the solutions. We're talking about an x number and a y number. So one of my solutions is 0, 2. Another is 1, 3. Those are just two solutions. But if I tried to describe my solutions as all real numbers, well, what number am I talking about? The x or the y? Yes, it's true that the domain is all real numbers. The possible x's is all real numbers. The range is all real numbers. All the y's can be any number. But when you're talking about the solutions, it's two numbers at once. And they're not the same number every time. So the solution isn't all real numbers because it's more than one number at a time. And those two numbers aren't the same. So it's kind of a convoluted explanation, but it's slightly different when you have a solution you're talking about that's two numbers. You're not going to say it's all real numbers. If you're talking about one type of number, the x's, you can say the domain is all real numbers. If you're talking about one type of number, the y, you can say the range is all real numbers. But if you're talking about the x and y at the same time, you call it a solution. It's an x comma y ordered pair. And there are infinitely many of those solutions. So that's why it's slightly different than all real numbers, and we call it infinitely many solutions when we're talking about both numbers at the same time. When you're solving an equation, we're just thinking about the x value. So we can say the x value solution is all real numbers, any number. Okay. Any questions about that before we do the yellow sheet real quick? Okay, I'm going to quickly pull up Desmos. Well, I'll do that. Yeah, I'll do it right now.
No, I don't do it in Stanton.
Okay, and if I make a table, or if I make a table for this one and I make a table for the other one, you'll see it doesn't matter what x value I plug in, the y values are always the same. That is how you know it's infinitely many solutions. Okay, on to the yellow sheet. Okay, we're going to quickly fill in the blanks here. First, for one solution. If there is one solution to your systems of equations, that means that there is one ordered pair that both lines share. So there are two lines that intersect at one point, or one solution. This point represents, again, the solution to the equation. For a table, there's only one x value. Oh, wait, no. Never mind. There's only one x value that makes both sides of the equation have the same y value. So there's only one row in the table where the x can be plugged into both equations and have the same y value. The last part is for an equation. So if you have an equation or a system of equations, let's look at our first example. Y equals negative x plus 4 and y equals 2x minus 2. You'll notice that the first equation is equal to y. So if I wanted to substitute y for negative x plus 4, I could do that because y is equal to negative x plus 4. So if I replace y with negative x plus 4, that was a valid substitution, like we did with some of the literal problems we had in the past. So if I replaced y with negative x plus 4, now here's a third way I could potentially find my solution. I can solve it. So if I add x on both sides, I get 3x, and then I have 4, and I have negative 2. And then if I add 2 on both sides, I get 6 equals 3x. And then if I divide both sides by 3, I get 2 equals x, or my solution is 2. And then if I were to take that x value and plug it into one of these, so if I plugged it into the second one, y is equal to 2, and I'm going to plug in 2 for x, times 2 minus 2, y equals 4, minus 2, y equals 2. So, essentially, you can set the two equations equal to each other, solve it, find the x value that makes these two equations equal, and then plug that x value into one of them to see the y value that goes with it. And now you have the ordered pair 2, 2, because the x is 2, the y is 2. And there's only one of these ordered pairs that makes both equations true. This method is actually not one you need to worry about for this upcoming test on Friday. We're just concerning ourselves with graphs and tables. But since there was this column here in the notes, I thought I'd at least introduce you to the method called substitution that we'll go over when I come back after Thanksgiving.
Dang it.
The last, or the next one is no solution. So when you're graphing, there are two parallel lines because no value of x produces the same y value for both sides of the equation. So they never intersect, so they're parallel. You could say there are no intersecting lines. You could also describe it that way. However you want to fill in the blanks. The table, there are no values for x that make both sides of the equation have the same y value. So if we looked at the table, doesn't matter what x value we plug in, the y's will always be different. And then if you remember solving equations that have no solution, when you cancel out all variables, it will create a false or invalid statement, like 2 equals 1, which it does not. So that would be an example. And I'll write here x equals 2 would be an example of an equation that has one solution. With infinitely many solutions, the last type, there is only, or there appears to be only one line because any value of x produces the same y value for both sides of the equation. So I'm going to draw a little picture actually for all of these. These two lines cross. These two lines don't cross. And this line appears to be only one. For the table of infinitely many solutions, there are infinitely many values for x that make both sides of the equation have the same y value. And then lastly, for an equation, when solving is complete, all variables cancel out, and the values remaining create a true statement, like 1 equals 1, or 0 equals 0.
Oh, finally.